So you should now have a splash that it is being recorded. And now if I go here, okay, Dave, try moving the mouse and you should have control of this. Okay.
I'm moving the mouse, and the question is...
Now if you do down arrow.
I'm not moving this. Oh, did I move that slide? I guess I did.
Yes, you did. So you have control.
All right, good. All right.
All right, sir. So we are recording. So.
All right. This morning we're going to present a webinar on the measurement and verification of savings related to the DOTA project. And we're going to be covering a number of topics: the purpose and benefits of measurement and verification, how to understand savings and guarantees, the criteria for a good M&V plan, defining baselines for performance measurement, understanding savings uncertainty, baseline types and metering. We're going to give some examples of M&V challenges on the DOTA project. We're going to talk about stipulated savings. We're going to also discuss and understand the different M&V options that are available and which ones were used on this project and why. We're going to give some technical savings examples on specific ECMs, and we're also going to discuss how to achieve high performance and how to monitor savings performance over time, and also the need for a partnership between DOTA and the ESCO in order to maximize project performance over the long term. So what is measurement and verification? It's a procedure involving the on-site collection of data on the performance of building energy-consuming equipment according to an approved measurement plan. So that's a very broad-based definition, but it's something that gives you the fundamental idea of what measurement and verification is, from a process point of view. Now, what are the purposes of measurement and verification? Well, one is you want to reduce future utility consumption and costs, and you also want to reduce future operation and maintenance costs. Both of these are important because you're trying to bend the cost curve of life cycle cost of operation of the facilities and equipment within the Department of Transportation airports. But it's used also for a legal purpose to evaluate the contract's guarantee performance to see whether or not JCI has any liability in case there would be a shortfall of savings. Also, though, this data can be used to leverage better performance over time and use the data that's coming out of the M&V process in some cases to improve future savings. And the chillers are a great example of that, as are also the VFDs for the ventilation fans. And there's another thing, which is an indirect benefit, but a significant one to building operators, and that's to improve the operational control of facilities. Now, you're going to collect a bunch of M&V data potentially, and how is that data going to be used? Well, we already talked about comparing utility savings, but also it's going to be used to calculate and predict savings information. So in other words, you might collect a certain amount of data, but then that data is going to go into a formula and be combined with other variables and factors in order to estimate or calculate what the savings actually are. Also, the data is used, as we mentioned on the previous slide, to determine whether the guaranteed savings have actually been attained per the contract and per the M&V plan contained in the contract. Very important to understand, an M&V plan is a contractual document. It defines what the ESCO is going to do in order to satisfy the guarantee definition that's contained in the contract, which is both sort of a legal but also a technical and economic definition of the guarantee. Then the M&V plan will actually generate the data when the M&V plan is implemented to determine how savings are to be estimated, calculated, and measured. And in some cases, that data will also be used, especially where things related to savings adjustments occur, to quantify the actual savings based on changes that may have occurred in the facility that are not necessarily directly related to the ESCO scope of work. And we'll touch on a number of examples of that later on. So, there's fundamentally several savings types. One is energy and demand, and those are very significant for this project. Electricity, both the consumption of kilowatt hours and the reduction in demand charges or kW charges are very significant sources of value for this project. And we'll see some examples of that a little later. But also, if there were any fossil fuel savings, which in this particular project there aren't any really significant fossil fuel savings to speak of, but if there were, that would be another potential source of savings value. But there are significant maintenance savings on this project, primarily from the reduction of the cost of future maintenance contracts. There was a baseline cost of maintenance that was being provided by JCI, and Airports was able to negotiate a new scope of maintenance which reduced future maintenance contract costs going forward, but actually improved, I believe, the quality of maintenance that would be provided for the project. Also, there will be some savings from materials, equipment, and replacement parts, even though I think that largely JCI is not monetizing those savings. Is that correct, Larry?
Yes, that's correct, Dave. A good example of that would be the lighting for the T8 bulbs, is that we did not monetize any material savings for that.
Exactly. And there's actually another type of savings that isn't on this slide, but there are time savings for operators due to improved equipment operation. And that's hard to put a number on, but if you don't have to run out to the field to look at a piece of equipment because you can see what's going on with it remotely with an energy management system, that saves significant amounts of time potentially. Or if it allows you to diagnose a problem through fault detection of what's going wrong with a piece of equipment that's not meeting its performance target, that also may save you time and ultimately money, because you get greater labor productivity out of your existing staff because they are freed up to do other things rather than just chase problems all the time. And last is water consumption, which, due to changes that occurred in the rate and availability of water savings rates, I'll say tariff alterations from Honolulu Water Department, that really, the savings that were originally calculated in the audit were not able to be realized. It's not economic to realize them any longer. So I think it would be fair to say there aren't any really significant water savings in this project anymore. Is that correct, Larry?
Yes, that's correct.
Yeah. All right, now, a little more fine-grained detail on operation and maintenance savings. There's reduction in internal labor costs, which I just talked about a little bit, but those are very hard to monetize. The reduction in outside labor costs through maintenance contracts are savings that are actually being monetized in this project. But there's some other benefits that are here we didn't talk about explicitly, but some reductions in scheduled maintenance because you got brand new equipment that won't require perhaps as high a level of service, plus reduction in unscheduled repairs, once again, due to having brand new equipment. Also reductions in repair parts and materials, because once again, you're dealing with new equipment. And also by standardizing your inventory of the types of lighting fixtures, for example, you're probably going to be able to substantially reduce your inventory costs over time. And one thing that I didn't mention on this list is actually extended equipment life. I mean, it's, once again, a little hard to put a direct value on that, but when you look at things from a life cycle cost, if equipment lasts longer than your old equipment, or you extend equipment life by having better control, better operation, better maintenance, that's a real value to DOTA. And one question you always want to ask is, can the actual O&M savings be verified? And would the ESCO reimburse us if there was an O&M savings shortfall? In this case, most of the savings are simply contractual savings from a renegotiated O&M contract in terms of what's actually being, monetized to justify the project economics. So these are very straightforward, pretty easy to compute. Now, when you think about M&V, there's the initial phase of M&V data that's collected during the investment grade audit, where you're trying to define the baseline for the different ECMs. And then there's also M&V activity that goes on during the construction period. Once particular components of ECMs are installed and they're starting to save energy, there may be field or spot measurements, as for example, in the case of lighting with this project, a lot of data collection and measurements of lighting samples of circuits, find out what the post-construction KW was. And during the IGA stage, there would have been measurements of the pre-KW consumption of certain lighting circuits. Now, there's also modeling of particular functions, of particular ECMs where individual building simulation modeling was done. There's also a fair amount of savings that were done with spreadsheet calculations because the savings were not so complicated. They were relatively straightforward. They were able to be modeled reasonably accurately in spreadsheets. And there was also a look at utility costs and consumption profiles because that was relevant to understand the behavior of the building, especially during the audit phase, and get a handle from an end-use model point of view of what was going on, especially in the computer simulations for certain ECMs. And we'll talk in more detail about that later on. But there is a shift as you move from those initial stages of M&V, where you're taking measurements during the audit phase or during construction or immediately after construction. In the long term, M&V will shift focus from meeting the guarantee to optimizing savings performance. And that's where the goal is continuous improvement in project performance over time. That's when trend log data from the EMS system and O&M strategies will become very important for exceeding the guarantee performance over time. Now, in those initial stages, there may be metering or measurements that are deployed during the audit. And why is this useful? Because you get accurate data to support your savings calculations. You also understand how the systems are operating and what the constraints on those systems might be. And that initial data can also assist you in determining which M&V option is the best method for that particular ECM in order to measure savings. And there can obviously be a difference in what method you choose based on whether it's a constant or a variable load. Something like lighting, ignoring for the moment the idea that you can control lighting, is something which is relatively constant unless you're actually changing the schedule for lighting, and then the load will vary according to the schedule changes. Now, in the case of your project, you found an opportunity to actually reduce and shave back the lighting levels a little bit as well. And so that's another opportunity to reduce the energy consumption by lighting. But in general, lighting is considered a relatively constant load, although there are opportunities to reduce lumens in some cases and still meet foot candle standards, and also to schedule the lighting with things like occupancy sensors or other controls to avoid having lights on when you don't need them on. And generally, the savings from lighting are a little easier to model than things which are inherently a variable load like cooling systems or chiller systems. And we'll see that a little later on when we go back. But once again, a lot of this data is collected for the purposes of establishing what is the baseline. And why is this important? Because the audit is really the foundation of the project, technically and economically. You want to have good, high-quality measurements. And in this case, Johnson took a lot of measurements, particular pieces of equipment, fairly large samples, so they had a good foundation to determine savings. One note that I would point out is that there's not a lot of annual metering. There is some of it related to the PV system, which we'll touch on later, but the reason people don't use a lot of annual dedicated metering in what's called option B is, generally speaking, it's just a rather expensive option. And hence, there tend to be other ways to get to where you need to go without deploying option B, although in some cases, like in a solar installation with PV, where you've got new output and you're not changing consumption, of existing consumption, you're basically replacing existing consumption by generating and producing new power with a PV system. And we'll touch on that more later. So, what are the benefits of good M&V? Well, really, you can see with a green line, here you would get savings over the 100% mark and maybe as high as 120% over time. That's the percent of savings you realize perhaps with good M&B. With poor M&B, you might see savings degradation over time and maybe lose as much as 20 or 30% of your savings, especially as the years roll by and controls get out of calibration or equipment's not properly maintained or operated, and then you start losing your opportunity to avoid future utility consumption. The goal here is really to maintain the original design performance of the equipment and not to permit drift and degradation of the controls or equipment's inherent efficiency. So what are the benefits of M&B for management? Well, it gives the agency greater confidence in the project benefits and leads to future projects. And in fact, at the OTA, that's already been the case. The Phase 1 project is essentially completed and constructed now, with the exception of the OSD pipeline scope. But they've already entered into a contract for Phase 2. Additional substantial amount of lighting and PV work has just recently closed as a project. Some other general things that it helps you with for managing your capital assets going forward is it's very helpful for prioritizing future projects and their benefits. And it helps you manage future utility and capital budgets. Sometimes that's not always appreciated as a benefit of M&B, but it really is one. For example, on this project, airports discovered some substantial need for more HVAC repairs that weren't readily apparent until there was the effort to fully implement some of the strategies related to the chiller system and the HVAC systems, and they found that the condition of some of the HVAC equipment was not as good as they had hoped. Also, you need data that's collected in the M&V process in order to make baseline adjustments if needed. You need to collect data that allows you to see what's happening in time that might affect your measurement process or a new load that comes into the equation. Also, if you want to sustain performance over time and continue to avoid utility costs out into years 15 or years 18, you really need some sort of ongoing tracking and monitoring of what's occurring with many of the ECMs, especially the ones that have more variable loads. Now, one thing that's important to understand about M&V data, and sometimes people think, well, this is just for the engineers. Nobody really cares about it. And while it's true the engineers are perhaps the most eager to take measurements and see how equipment's performing and track technical savings performance, it's also true that the budget staff is interested. Why are they interested? Because they're interested in how it's performing relative to the financial performance of the savings guarantee. And they like to see the data that's available to support that the guarantee was satisfied. But it's also useful to agency executives and legislatures to take credit for the project and see what benefits are produced from the project and help quantify those, especially economically, and to help them manage going forward, once again, the overall performance of their buildings and facilities and equipment. And last but not least, it may provide data that's required to claim utility incentives because you have to demonstrate that you're producing a certain level of investment in energy efficiency technologies in order to claim those particular incentives. So, also, another perspective on M&B that's sort of important is that what about the building operators? Well, if you can reduce nuisance calls for hot and cold calls for particular zones because the equipment is better operated and maintained and controlled, that reduces their workload. If you can, through remote monitoring of performance, get a better handle on what's occurring with your equipment and a better understanding of what's occurring with your equipment, maybe you can be more effective at how you operate it. And you can improve both the reliability and the control of the schedule of the equipment, for example. Some other benefits for operators of equipment is that it allows you the opportunity to optimize system performance over time. For example, the kW per ton of a chiller system, which is particularly important for this particular project because there's a fairly substantial amount of savings associated with optimizing the kW per ton of chillers. The existing chiller baseline kW was about 1.1 kW per ton, and it's being reduced to 0.773 kW per ton currently, and probably it's going to improve over that as we fully implement the optimization strategies as the OST pipeline work is finished. But even the initial reduction from 1.1 kW per ton to 0.773 kW per ton is like a 30% reduction, which is very substantial. Also, as I noted earlier, benefit for operators, if you can reduce breakdowns and equipment repair costs, that's a benefit to them. If you improve indoor environmental quality, try higher quality lighting and better control of cooling, you may reduce building occupants. You may reduce complaints from building occupants, and that's a benefit as well to operations staff. Also, it gives you timely feedback on how the equipment is performing, which allows the maintenance staff to direct their resources more effectively to maintenance tasks. So all those things are benefits of M&V data for building operators. Now, one of the things we don't often think about is that first cost of equipment, the price of equipment that we buy and put into facilities, are typically only 5% of the life cycle cost of equipment operation. So there's all these other costs that we really care about. Even though if you're just looking at a purchase order, you may only see the price of equipment. Oh yeah, that piece of equipment's $10,000. But if I look underneath and I say, well, that equipment exists over time and it's going to be in this facility for 15 or 20 years, I might also care about, well, what are the costs of the future failures of that equipment? What are the costs if there's a startup delay for that equipment? What if there's a performance problem with the equipment? How does that affect the cost of operating that equipment? The energy costs, the obvious thing. I mean, it's going to use a lot of energy over those 15 or 20 years, and how much it's going to use figures into what the life cycle cost of that equipment is. And is it going to deliver the service that I want? Is it going to produce the light level? Is it going to produce the occupant comfort that I want in terms of air temperature, in terms of ventilation effectiveness, etc.? So there's all these other factors that we need to be thinking about when we think about optimizing performance over time. Now, if you just look at purely, strictly from an M&V engineering need, M&V allows you to quantify changes pre- and post-installation for specific ECMs. What was it like before we did the project? What is it like after we did the project? How did it change? We may be taking spot measurements. We may be taking samples from big population of similar equipment. And also, we may be going back and doing some sort of annual inspections to check, to verify the technical potential that the equipment we put in, and when we took these pre- and post-measurements, post-measurement equipment is still in place, it's still operating properly, and it's still generating the savings as we go forward in the future. So the fundamental, in a very oversimplified way of thinking about the engineering need of how you figure out energy was saved, or how much energy was saved, is you look at what's the baseline, however that's defined for a particular ECM, what are the measured and calculated changes from that baseline, and what positive or negative adjustments have I had to make to savings which are related or unrelated to those measured and calculated changes. And I'll just draw your attention to that item in red, which is for large variable loads with interactive effects. This simple equation here may get rather complex. You may be looking at a lot of pages of spreadsheets, you may be looking at a lot of variables, or at least, half a dozen or 10 that are insignificant. And so while this gives you a picture, it's a somewhat oversimplified picture of what's involved in the engineering aspects of M&V. So, understanding savings. We all think that we understand what savings are, but there's really savings evolve over time, and this is like a way of thinking of what savings means at different points in time. When the audit is done, there's a prediction of how much savings each ECM is going to produce, and usually those are accurate within plus or minus 5 to 10%. Usually, the ESCO, in this case JCI, is going to guarantee not 100% of their predicted savings, but something that has a safety margin that's usually 5 or 10% below the predicted savings to provide that safety margin. So if there were 100 units that they thought they were going to save with a particular ECM, they might guarantee 95. Now, refresh my memory, and for this project, Larry, would you say that there were some measures that were 95 and there were some that were maybe a little higher than that?
Yes, actually, Dave, it's the other direction. Is that for lighting we guaranteed 95%. Most of the AC, ECM2 and 4 we guaranteed 90. So overall, the blended guaranteed factor on the project was about 92%.
About 92%. So right in that range of 90 to 95, depending on the measure. Yep. And then you have, so those are sort of two things. That's the audit phase, and then there's the contract phase, where you put a particular guarantee in the contract and say we're going to guarantee this level of savings. Now we actually determine verified savings, and already JCI has actually produced 3 reports, one for construction year 1, one for construction year 2, and one for the stub year, which is a half a year. And the verified savings in every case exceeded the actual guaranteed savings, which is not a shock, as we predicted that actually the audit said savings should be 5 to 10% higher than what JCI was willing to guarantee because of the safety margin. Now, the actual savings, though, could actually be verified, or could actually be different than verified savings. People say, well, how can that be the case? Well, verified savings are determined by following what the M&V plan says to actually do to calculate savings, which is what JCI is contractually obligated to do, and they did that. And that's how they came up with savings. But remember, any savings that's given by any ESCO, JCI, or anyone else is conditional guarantee. It assumes that proper operation and maintenance of equipment occurs, and the condition of equipment is what was there at the time that the audit was done. If it was equipment that was not part of the scope of the original project. Well, when either of those conditions are not true, that may cause actual savings to actually be less. And in this case, they found situations where HVAC equipment was not in a condition to be totally effective because there were some things that were not functional about it, that weren't part of the original scope of the project, that limited and reduced actual savings. There were also just some scope changes when you got into the details of lighting, for example, that required you to substantially reduce lighting scope. Now, there was also some additional new lighting scope added that picked up those savings. But net, I think, at least for phase 1, there were probably some actual savings that were not available because of some scope reductions. Would that be accurate, Larry?
Yes. Primarily as an example of that is Custom and Border Patrol area was de-scoped for lighting at H&L.
Yes, great. Now, when you think about M&V, there's sort of 2 ways to think about it, and sometimes this distinction is lost on people. One thing is the EPC contract defines a guaranteed savings number, which is a meter exceed legal requirement for the ESCO, which if there's a shortfall, they have to write a check to DOTA. So that's the legal scorekeeping part of the guarantee. But there's also optimization over time. Large variable loads like chillers provide an opportunity to really increase and maybe exceed the guaranteed savings level. Remember, if JCI had a 90% ratio of guaranteed to projected savings, that means there's maybe 10% or even more upside if they were to actually hit what the audit number was. So there's an opportunity over time to optimize those savings, and that ought to be the goal. Let's go get them. We know that there's variability in performance, but let's see if we can optimize control and maybe pick up some extra savings going forward. So, what is the contractual need for an M&V process? Well, remember, scorekeeping, so when you define savings and savings uncertainty or savings risk, you want to design your M&V process to a desired level of accuracy. And by providing that safety margin, which JCI did in this contract, that's one way to manage performance uncertainty. That means, hey, even if there's a little shortfall from what our audit projected or estimate was, we still meet our guarantee because we have that safety margin in there. But also, and we touched on this in the previous slide, we allocate the savings risk responsibility between the ESCO and the agency. There's certain things that the agency controls, and there's certain things that the ESCO controls. The main thing the ESCO controls is what equipment they put in, what maintenance services the ESCO is contractually providing. But building operators still have a lot of leeway in what they do, and those are things that the agency controls, and those can have a significant impact on savings performance. A great example of that is that the VFD fans, which provide a tremendous amount of energy and demand savings, when they were originally put in, JCI had a goal to control them at a certain speed to produce the savings and avoid future consumption, but some of the building operators, in order to get cooling in an outdoor zone, drove those fans or overrode the fans to run them at higher speeds. Well, that might have produced some quote-unquote cooling effect for them, but it did it at a high energy penalty. And it wasn't necessary because the primary purpose of those fans was to reduce noxious gases from vehicle exhaust. And the fans could satisfy that requirement at a much lower speed. But the other thing in the contract that you're doing is you're defining the guarantee evaluation process and procedures that will be followed legally and, technically and economically, and how you determine whether that scorekeeping function has been fulfilled, whether JCI met their guarantee. So one question that is at the heart of M&V is how much measurement and verification is enough. And usually the answer here is, well, we can always spend more money on M&V. We could put meters on everything, but it would be exorbitantly expensive. So what's the right point where you trade off cost of M&V versus accuracy of M&V? And as you watch what happens to the certainty of savings over time, you reduce the uncertainty of savings over time. The value of information that you're getting from M&V starts to decrease as you get more and more information, but the cost of M&V goes up and up, and eventually you hit a balance point where there's diminishing returns. In other words, the next dollar that you spend on M&V, you're going to find out, I didn't save 50 cents, but it cost me $1 to find out I didn't save that 50 cents. Well, that wasn't a good investment. Now I've reached the break-even point. Now, this is conceptual. In a real project, probably it's not going to look exactly this precise and perfect, but in a more chunky sense, you can definitely see that where once M&V costs go over the order of like 5% of the value of annual savings, you're probably starting to get way up there on what M&V cost should be. Or in some cases 10%, depending on how complicated the particular ECM is. So what are the factors that affect the cost and appropriate level of M&V effort? Well, one is obviously the value of projected ECM savings. In this project, we've got millions of dollars of annual savings. So, someone said, I think we can do all the M&V on this project and it's only going to cost us $10,000. Say you're probably crazy because it's way too complicated. There's way too many things to measure. There's a lot of complicated monitoring that's going to be occurring going forward. There's no way. And the value of the projected savings here are very large. So if you can improve the value of the savings by 10%, maybe that's $300,000 extra dollars a year. Well, that's a lot of money. So it's worth spending some money on M&V. But I already touched on how complicated is the ECM's performance. How many different ECMs are there? Because every ECM, if it needs its own M&V baseline and plan, will cost some money. If you did 50 ECMs, you're going to spend more than if you did 2 ECMs. The other thing you have to pay attention to is how much do the ECMs interact with each other. Well, in this case, when you put in LED lighting and you replace fluorescent lighting, it turns out that LED lighting has a much lower thermal waste heat output, So you take a lot of load, at least in zones that are cooled, you take a lot of load off the chillers. Those savings are actually substantial. Now, in a different climate zone where there was a significant heat load, that might not really help you, because even though you'd get savings by reducing the cooling load from the waste heat from lights, you'd pay a penalty to the extent that those lights were contributing free heat to your heating load in parts of the year. But in Hawaii, that's sort of a non-issue because you don't really have a heating load to speak of. So LED lights here are almost a perfect application because they pretty much just reduce your chiller load all day long, all year long, pretty much. The other thing you pay attention to is how uncertain the savings are. Technically, certain technologies just have much more variability in their savings performance, and others are relatively straightforward. But a good example of fairly straightforward savings are the high-efficiency transformers. You put those in, you do one-time pre- and post measurements, and then you periodically check to make sure they're still in good condition and operating, and those savings are not that uncertain, and it doesn't pay you to spend a lot more money measuring and verifying over time or going back and taking repeated measurements, because there's just not that very much variability in their performance. Another thing you want to pay attention to is what other value do they get from the M&V data? Well, if it helps you target your maintenance or improve the operation and control of equipment, that's a secondary value from having, for example, the energy management system. So, where does a good M&V plan come from? Well, I say negotiation. What's really important here is for the customer to understand what the ESCO is going to do, why they're going to do it in the M&V plan, why it makes sense technically and economically, and that they reach a real agreement. All right, this is how much I'm willing to spend on M&V. This is the level of accuracy that is acceptable to us for a baseline. We know the plan can be effectively implemented, and I understand how the guarantee provisions work. I understand that it's an aggregate guarantee. While one ECM might overperform, another one could underperform, and that happened on this project. Where at least in the beginning, we were not able to claim some of the savings from the PV system because of delays in getting the utility interconnects in place. So we couldn't count the savings from those. And the water was another one where, because of changes in tariffs, JCI was not able to count the water savings. Fortunately, they were able to make that up on the lighting savings and savings from the VFDs. But all of these things go into it. Is the equipment being operated properly? Is there enough data collected to adjust the baseline? And is there enough information about how training and maintenance are going to play into it and support the M&V plan? And that's obviously a thing we'll talk about a little bit more later. So, we already touched on this earlier, but what is a good M&V plan? These are some of the criteria. A good balance between savings and measurement, savings accuracy and measurement cost, complete and conservative calculations that capture all the significant project effects, and relevant and transparent presentation of data and calculations. This is something where I actually wrote a whole report for DOTA on sort of the M&V process. I guess it was about 15 pages. I shared it with JCI. I suggested a way that they could present a lot of their data in tables that would make it more user-friendly to review. And JCI, in their, I think it was in their year 2 and maybe their sub-year, they started presenting the data in that fashion. And it made the review process a lot easier to evaluate the savings performance on the projects. So it's important when you're getting an M&V plan that building operators have an understanding of this, and building maintenance staff understand and buy in how the M&V process is going to work. It also, the M&V plan identifies what data is going to be collected and how it's going to be collected, which variables have the biggest impact on the energy use of an individual ECM. In the case of lighting, for example, how many hours it's on has a really big impact on how much energy is used by the system. Provides time intervals for measurements where you're doing trend logging, for example, of the VFDs on the ventilation fans. That's trend log data that's very critical to finding out what's actually happening with the speed of those fans over time. And it also lays out, what's the budget for M&V, what equations and what models and assumptions am I using, what data is it required to complete the M&V plan. So also it specifies the details of the pre and post measurement actions. This is what we're going to do before the measure is completed, what we're going to measure, and this is what we're going to do after it's completed. Who's going to be there to witness the measurements or review ESCO calculations and reports, and who's going to identify how changes to equipment control strategies or maintenance practices are affecting the optimization of savings over time. So another thing is looking at how M&V trend data is going to be used to evaluate and improve project performance. And I know we've had several discussions on this already with especially the chiller optimization, and there'll probably be more in the future as we figure out the strategies to bring forward and get it, especially when the OSD piping project is completed, how to bring about the optimal performance of the whole chiller system as a system, not just individual chillers on their own. We will also be looking in the M&V plan how delays in the project implementation impacted the savings guarantee. In this case, there were some significant delays, particularly related to the PV systems being able to come online. There were also, just going back to that previous slide, which we talked about already, some significant changes, especially in the lighting scope, that I think, at least initially reduced savings by about as much as 100K or in that neighborhood. Now, JCI's M&V plan spelled out how devices would be calibrated, measurement devices, and they actually provided proof of that calibration to show, hey, this is the device we used to take this measurement, and this is how we calibrated the accuracy of that device. So you know that the measurements we're getting are good measurements. And another thing that's useful is to show a sample periodic savings report, which contains all the data, calculations, summary results, and allows you to view sort of ahead of time, oh, okay, this is the type of data I'm looking at, and this is how I have enough interpretive narrative to explain the contents of what that data means. So, having clearly defined specific measure and project performance standards is really essential. Why? Because if you don't have clear performance standards, it leads to misunderstanding and confusion, or if it's ambiguous, it can be interpreted in multiple ways, and people will look at it differently and they'll come to different conclusions. So, very important. Last bullet here, why should the measurement standards you agree on be fair, efficient, technically sound, cost-effective, transparent? All that stuff I think is pretty easy to understand. This last one's a little bit of mystery to people. They go, well, why is it consistent with standard industry practices for M&V? Because if a standard is not articulated specifically in your contract, you're ever having a dispute about the savings, an arbitrator or a dispute resolution panel is going to look at what standard industry practice and see if you're consistent with it or not, if it's not defined in your contract. So, we already touched on this first bullet, that cost-effective measurements got to produce data with a value greater than the cost of measurement. Pretty obvious, but still a very important point to make in that trade-off between cost and accuracy. The second bullet, also really important, it's got to be consistent results no matter who uses the measurement and verification procedure. You shouldn't give it to 5 different engineers and they follow the procedure and come up with 5 different answers. Then your procedure is underdefined because you're not getting a consistent result by following the M&V process that's articulated in the contract. Also important that M&V reports produce timely results. Because why? Because if you're producing data showing that something's deviating from its savings performance targets, you want to know that within 30 days. You don't want to find out 6 months later, oh, guess what? We lost savings for 6 months because we didn't meet our performance target because the equipment wasn't operating right. You want to be on top of it more rapidly. And just contractually, there ought to be a process for resolving any disputes over measurement issues that is defined in the actual contract itself. So, Another dimension is, okay, you've quantified the level of consumption savings, but now how do you economically value those savings? We want to use accurate utility costs. Now, typically those will be defined in the contract. At the investment grade audit time period, whenever that was, there were certain utility rates in place. Normally, there will be escalation rates applied to those based on historical practice, which was done in the case of this contract. Those escalation rates will be used to value future avoided utility costs. Why is that done? Because it's not reasonable to assume utility rates will stay the same for the next 20 years, and there won't be any escalation. And if you were to make that assumption, you would undervalue future avoided utility costs by not using escalated rates, and you would not make the proper and appropriate economic investments in your energy performance contracting project. So, not giving you, I'm not shooting to make absolutely the detailed penny for penny or dollar for dollar, but I just wanted to give you just a sense of how the utility rate schedules vary by the particular DOTA facilities. Some of the small facilities just have a high kWh charge, but no kW demand charge, maybe 35 cents a kilowatt hour. Medium facilities have lower kWh charges for energy, maybe 30 cents a kilowatt hour, but have a significant demand charge of $12 a kW for demand. And the large facilities have lowest kWh charges, maybe 28 cents a kilowatt hour, but the highest demand charges on the order of $25 an hour, kW for demand. Well, you can see the ability to save demand, especially in those large facilities with the big demand charges, is commercially a lot more valuable than, and obviously if you get into a small facility, you save all the demand you want, it's not going to give you any benefit on your utility bill. All right, so what are some of the sources of data for savings calculations? Well, one is the trend analysis from a building EMS or dedicated control system. Also, it can come from short-term metering, like, for example, lighting circuits, or short-term measurements of circuits. You can be looking at utility meter billing analysis. There was some of that done on this project, especially in year 2 savings, to look at the 2011 utility meter billing analysis of consumption and then comparing that to the 2015 and making all the adjustments for the ECMs that went in, and then looking at the actual data, but then looking at all the other changes and factors which are required if you're going to do any sort of utility meter billing analysis comparison. And there were many changes, like the weather was different, occupancy was different, and an increase in occupancy, I think at OTT was like as much as 20%, which is huge. Great for the airport, but it puts a much bigger load on the chiller system. Plus, there were additional energy-consuming pieces of equipment that were loaded into the system. And also, there were a lot of meters that weren't even the topic of this particular project, but that were included in the consumption comparison to some extent. And actually, you need to exclude some of those meters in order to really get the baseline comparison correct. There also can be computer simulation data, which was used in part, when the utility bill meter analysis comparison was being done in eQuest, which we'll talk about a little more later, which is computer modeling for energy savings software. So, eQuest is a quick energy simulation tool based on a DOE model, Department of Energy model. It's been widely used for many years by ESCOs. And it simulates annual energy use of a building by accounting for the interactive effects between different building systems. This is one of its primary virtues because it allows you to actually see what's going on in a particular building and sort out the effects. And usually with eQuest, you're doing a certain amount of calibration where you're looking at historical utility data, you're looking at how you modeled the building with your user-defined inputs and the default inputs, and then you're running a model to see if it can produce the historical utility consumption. And if it does, within a reasonable accuracy, say plus or minus 5 or 10%, you know you've got a model that's giving you a reasonable picture of how the building performs. And then you can make changes to the model and see how that affects the consumption from specific ECMs. So what eQuest shows you is how to maximize whole building efficiency by seeing which ECMs produce how much savings. And you can sort of put one in, take one out, see what it does to the overall consumption. And eQuest is built based on both user-defined input variables that are site-specific to your facilities, but it also looks at default inputs that are inherent in a particular building characteristic or occupancy or particular physical systems that are in the building. And the nice thing about eQuest is it allows you to look at model outputs that show the consumption by end user equipment type. This is very helpful to the ESCO in modeling what the likely impacts are on savings of particular ECMs. So in the DOTA savings calculation process, spreadsheets were used to model and calculate 46% of the dollar value of savings, but the eQuest model we just discussed was used to calculate about 35% of dollar value of savings, and PVSys software was used to calculate about 19% of the dollar value of savings. So this shows you that just a mix of methods were used in terms of what was appropriate for that particular ECM in terms of the cost-effective approach to model savings. So when we define baselines for specific ECMs, it's the mutually agreed upon sort of pre-retrofit annual utility consumption and cost for a building or, and in this case, this is the more appropriate thing, the specific energy using system in it. But one thing about baselines that's important, it's not just utility consumption in isolation, it's all the assumptions around that particular energy consuming system and how it operates. What are the hours of operation? What are the occupancy? In the case of cooling systems, what loads does it face? What are the set points for temperature? All those things have to be characterized in order to really define a baseline. Baselines are critical because they define the standards for technical and economic analysis of savings. So here are some sample standards, and this is my trick slide. There's something wrong with the slide, but it's not immediately obvious. It all looks logical. So we look at cars. We say, well, that's a type of energy-consuming system, and lighting is a type of energy-consuming system. And here's a performance vector for a car. We all think about when I buy a car, I want to know the miles per gallon. When I get a lighting system, I want to know how many lumens of light I get out per watt of energy I put in. But then what do I actually save? Well, in the case of a lighting system, it's obvious. I'm going to save energy, which I can measure in kilowatt hours. And maybe I'll save some demand, too. It would be kW, but I didn't put that in. But do I really save something? What do I really save on a car if I have a 100 miles per gallon car? Larry, do you know the answer to this one?
Yeah, it looks like the miles driven might be inaccurate there because the savings really would be in gallons of gasoline.
Exactly. Maybe I can drive more miles and use the same amount of gallons, but I'm probably not going to reduce the miles driven if I have a higher mile per gallon car. So it's analogous. Miles driven is more of a usage factor, but the actual savings is in the form of energy or gallons. So this is my little trick slide to make you think about it, process, what am I really saving? Now, in baselines, you can look at a lot of different baseline types. You can look at a whole building, utility meter data. In the case of these facilities, you would be looking at a whole lot of utility meters because there are well over 100 in all these facilities. You start counting them all up. And it turns out that in large, complex, diverse buildings, you're better off looking at specific systems with measured and calculated data, or in some cases, like the PV system, sub-metered data. Because that just gives you a better way to define the actual baseline for a particular energy-consuming system in the building. Sometimes you use models or calibrated simulation data, which JCI did with the eQuest model, with their spreadsheet modeling. And you may be collecting trend log data where you have a trend log that's the baseline trend, and then you want to see how you're going to change it over time, how you're going to change, for example, fan speed in the equipment operation, how you're going to track that over time. But very important to understand when you define baselines, especially if you're defining them for specific systems, which in the case of DOTA is pretty much everything is defined on a specific system basis. All the ECMs are defined that way, and their M&B plants are defined that way. Hence, their baselines are defined that way. But if you are doing baselines for a project, they should only represent the consumption affected by your project, not all the other utility meters, which the agency may pay utility costs for, but aren't really affected by the project, because that'll confuse your analysis. So, what are requirements for the M&V plan to adhere to the International Performance Measurement and Verification Protocol, which was developed by the DOE many years ago and is now stewarded by the Efficiency Evaluation Organization? A side note, when DOE originally developed IPMVP, I actually sat on the subcommittee for indoor environmental quality of the IPMVP. So, I was talking about this on a previous slide, but when you look at a baseline, it's not just the energy and demand profile, it's also occupancy, space conditions, equipment inventory, operating practices, and any existing significant equipment problems. All those things have to be identified to figure out what the baseline is and what should be in your M&V plan. Here's more variables. In your baseline, when you're looking at a specific system, current fan speed, operating hours, light levels, temperature set points, current level of O&M, degree of equipment control, all of these are variables that have to be thought of, and we tend to think, oh, I can just look at one number on my utility bill. No, you got to look at all these things. That's a lot of stuff to bear in mind, but you can't accurately define a baseline with just utility information. You've got to know all these other factors that are part of the baseline condition. And more importantly, baselines, depending on what ECM it is, are not necessarily stable over time. Some of them have significant annual changes. Some of them change rather slowly over a period of years, but they still change. You need to understand how the baseline changed over time, and you need to understand historically and how it may change over time going forward and why. That requires you to understand the variables that play into the baseline and affect the baseline. And that's why you need to know what factors are driving the variable loads, how much time and data I need to figure out and both define the baseline and then track what's happening with the baseline over time. And is there new equipment that's gone in that's affecting the baseline or affecting the performance of the new ECM equipment I put in? And if so, how is it affecting it? All these are things that need to be answered. Other things that have to be in the M&V plan to adhere to IPMVP is it has to specify the data that's available for savings verification by a third party. In that case, primarily me, since I did most of the review of M&V reports on behalf of DOTA. But also, there has to be a description of how non-routine baseline adjustments were made or will be made. In this case, there were a number of them which JCI put forward and described what they needed to do to change baseline or make baseline adjustments, and those are described in the particular M&V reports. Also, having a full understanding of existing conditions data is very important. Not only the operating logs for chillers, air handlers, other equipment, but EMS monitoring data to the extent it exists. Now, historically, and correct me if I'm wrong here, Larry, but I don't think the existing EMS system had extensive monitoring capability, so you probably didn't have a lot of baseline monitored data available from the existing fairly antiquated EMS system. Is that accurate?
Yes, that's correct. It was an early 90s generation system, and it really was stop-start and system monitoring, not a whole lot of trending, and not a whole lot of analog measurements.
Yeah, that's what I recall. But you also need to see, were there any occupancy controls on lighting? And if so, were they functional? Were they operating properly? Were there test or balance reports on air and water flows for HVAC systems? And if so, were there issues related to the functioning of the HVAC system? In fact, I think when you went in originally, didn't you discover that a lot of the dampers and some of the chilled water valves and stuff were basically failed in open positions or were not capable of being controlled by the existing EMS?
That's correct. The EMS did not, it's still an old pneumatic system, and we did find quite a few air handlers where the pneumatic valve actuator had been removed.
Right.
That out here in Hawaii left the chill water valve wide open.
Yep. A couple things that aren't even on here, but Maintenance records and costs are important, but also spot measurements of equipment efficiency might help you characterize existing equipment. But utility interval data might also be useful. And, that's just another example to the extent it was available and relevant to a particular ACM. Now, I want to get into some of the challenges to calculating an accurate baseline. Baseline analysis might fail to account for periods during which equipment was out of service. Well, how would this be the case? Because if you're looking over a historical time period and you were looking just at utility data, that's nice, you have the utility data, but what if some of the equipment was down during that period and you didn't know about it? Well, then that would skew your utility consumption profile. What about utility data itself? Believe it or not all utility metering, billing is accurate. I have seen errors. I've seen meters go bad. I've seen billing errors. I've seen data entry errors by utility companies. I'm not saying they're super common, but human error does creep into it. And, there are cases where, especially in this case, for example, one of the reasons 2011 was chosen as a baseline is because we couldn't get adequate, complete data on 2012 from the utility company. So there can be limitations when you're trying to define baselines. Sometimes the run hours of equipment are difficult to accurately measure, especially if you're trying to consider what historical run times were, and all you have is operator reports and people's memories. Well, if there's been staff turnover, people's memory may not go back that far, or their memory may be flawed, and you may not have completely accurate information on that. There may also be patterns of inconsistent operation of existing equipment or poor or manual control of equipment. All of these things can make it difficult to figure out what's happening with the baseline. Why is this important in savings analysis, and why does it make savings uncertainty? Because when people do sort of postmortems of M&V plans and M&V plans that are implemented, uncertainty in baseline definitions and existing conditions around that baseline is really a key contributor to future savings uncertainty. And so that makes the case for during the ITA, really document and get the best data you can on the quantity, condition, operating efficiency, and hours of everything that's in there now, so you have a good handle on that. Excuse me. Also, you want to specify your quality assurance procedures for the M&V plan. And what's the expected accuracy based on the sample sizes that you might do for certain ECMs, whether that's a frequency of trend log data, what's the size of your lighting pre and post samples. But you have to lay out how you're going to report out the M&V results, and what are other uncertainties that can creep in. Well, you can have errors associated with modeling input parameters or calibration. I know when we were doing the reconciliation between 2011 and 2015, JCI used the correct weather data file for one simulation, but for the other one they used an incorrect weather data file. So we corrected it, and it made a significant difference. But that was just a modeling choice. Sometimes spreadsheet calculations. I spent a lot of time with Jake going through spreadsheet calculations, and we discovered a number of data entry sort of errors. And when they were corrected, it made it improved definitely the quality of the analysis. But that's something, especially when there are multiple people involved in calculations over a period of years. Sometimes the handoff isn't completely smooth, and not every assumption or analytic choice is interpreted or explained in the best way. And so errors can creep in, which under review you discover, and then you have to correct them. So those are some examples of uncertainty. But it's also true that if you don't have supporting data for your engineering calculations, or you have incomplete calculations, sometimes when somebody's reviewing it from a third-party point of view, they may not be able to follow the analysis without asking you a lot of questions. What if there's missing data on equipment condition or operation, which we already talked about a little bit? Or just trying to, if somebody makes changes in the facility but they don't report them to the ESCO or anybody else, then you have a little bit of a detective challenge on your hand where you got to go track it down and find out who did what when and what was the impact of it. And that's always fun. Sometimes you're successful, sometimes you're not. What are some of the types of performance risks just overall from an energy savings performance contract? Well, equipment can degrade over time. Even if it's brand new now, 15 years from now, it may develop some issue, and that, unless you're on top of it from a maintenance operation and monitoring point of view, there may be a performance risk regarding savings. There can be mechanical or electrical failures. You can have a power outage, or you can have a mechanical breakdown. That can affect savings. You can have a control failure where controls are overridden and savings that you thought you were getting are not being received because controls were overridden by somebody. And instead of a short-term override, they were left in the override position, and then you lost savings for some period of time, sometimes undefined. What if the building use changes, or there's customer space or equipment additions? If I recall correctly, Larry, there's going to be some substantial additions to DOTA facilities over the next 5 or 10 years, right?
Yes, for example, at Honolulu International, they're going through the modernization program where they will be building new terminals that will substantially impact overall energy use at the facility.
Oh, absolutely. And, then obviously modeling that is something you have to take into account. So that's definitely a change in customer space or equipment conditions. Those will be very substantial changes in space and equipment conditions. But there's a couple of others that aren't even on this slide, which are, what about insufficient training or operator turnover? Suppose somebody doesn't have an effective or enough training in terms of the operation of the equipment, or even if you train someone, what if they get replaced and their successor now needs retraining because they don't know everything that they need to do, and there's a risk of them not taking the proper action to optimize savings. Well, what are some of the factors that affect reliability and performance over time? Well, there's system optimization for changes in the operating schedule or environment. So you can face a new load, but if you reconfigure the chiller to optimize for that new load, you can still maintain the best savings. But if you keep running with the same sequence of operations, that may not be optimal, and you may not get the savings you hope for. Also, monitoring savings over time, as JCI is doing, particularly on the PV system, on the ventilation fans, and on the chiller system, are very important sources of future value that you want to be tracking. Now, if you did a main utility meter baseline, which the only way we really used it on this project was sort of a cross-check on all the other contract-defined M&V methods, just to see if you looked at all the option A and option B methods that JCI was using to track savings from specific ECMs, and then you built up that with the actual utility data in 2015 and you compared it to 2011, you can do a cross-check. If you do, usually people like to use what's called an average year, where you take several years of utility data and create an average, 12-month average. But there's a problem with average years, is they can mask trends of increased consumption over time. And so they're not always as great a tool as people may think when you're trying to do baseline comparisons or cross-check utility meter data with option A and option B savings guarantee data. And you can have non-recurring events that can skew a baseline. For example, equipment can be broken but unreported, and it's, the system may be limping along, but you don't realize it's carrying a burden which is skewing the baseline in some way. So one thing that, because people are used to looking at utility bills and thinking utility bills will give me the answer because that's what I use to pay the utility company, well, main utility meters aggregate a bunch of different loads, and they're really designed to collect revenue for the utility. They're not really designed to manage your end-use loads or to do M&V for that matter. Although they can be a source of data for M&V, they are not the sort of panacea that people like to think they are. So why measure individual end-use equipment, which is a lot of what JCI did on this project for the airport's ECM? Well, one, you can isolate the affected end-use consumption from the total building meter. That's a plus because now you've removed it from a bunch of noise from other loads that are unrelated to the measures you're taking to save energy. Also, quantify the parameters for engineering calculations and simulation models, like if you're building the eQuest model. So that helps you, if you're building it up, you're taking some individual system measurements. And it provides you equipment operating diagnostic data in some cases. That would be true particularly of the chiller system and the VFD fans or the ventilation system. And it allows you to correct Cadillac data estimates. People who manufacture LED lighting say it's going to use this amount, but that's based on bench lab predictions. When you get it out in the field at actual temperatures that are in the field in the actual configurations, you want to take the post measurements to verify the actual performance of that LED equipment. And it allows you to focus on equipment-specific performance and allows you to make corrections at that level, which can be very helpful. So, if you do get sub-meter data, which in this case is primarily the PV system for which that's true, there are a couple possibilities. You can have a hardwired sub-meter, or you could have meter data via a network and an IP stored on a server, or you could even have a temporary data logger device, as you would, for example, on the lighting occupancy sensor or something like that. But baseline includes not only the energy, and I'm sort of repeating myself here, but also the measurements of all the pre-retrofit environmental conditions associated with that energy consumption. That's important to remember because nothing stands in isolation. Everything's connected to everything else. So what are some potential data errors that you could have even from measurement devices or meters? Well, your measurement device or meter can be inaccurate. It's a fact. I mean, water meters are a great example. They're notorious when they get old for running slow. And you replace a new meter and suddenly you have a big jump up in your water consumption, not because your water consumption really went up, but now you're actually measuring your accurate water consumption, and before your measurement was inaccurate. If you did calibration status of your measurement device, if it wasn't properly calibrated, but that's why JCI was required to show the calibration certificates for their M&V devices. Also, making sure you use the right measurement units. Water can be measured in gallons, can be measured in cubic feet. You want to be sure which one you're using. And same thing, if you measure savings from lighting, you can measure in volt amps in lieu of kW. And, you want to see if that makes a difference in what happens. Also, if you have a meter, an EMF system recording data, what if you lose some of that data or you get zero or null values? Well, then you're going to have to improvise. A couple other things related to potential errors or uncertainty. A lot of these relate to measurements that we're talking about here, but also you get sampling. In this case, JCI took robust samples of equipment, particularly the lighting, and on the transformers as well. That allows you to get more accuracy and reduce uncertainty. But also, we talked about the use of modeling earlier in the eQuest model, which is sensitive to putting in the proper assumptions and then calibrating the model against historical utility data to make sure you reduce the uncertainty there. And inherently, we've touched on this a number of times, there's just some inherent technology risk. Certain technologies are much more variable in their performance, and therefore that can be a factor when you're figuring out the best way to do M&V savings. So, one thing to remember about building sub-metering before you run out and start putting a sub-meter on anything is that sub-metering by itself does not save energy. It can be used for utility cost allocation, or in the case of a PV system, to measure production values. But even those production values have to be normalized for solar irradiation, for example. And you have to correct what comes off the sub-meter. You can't just look at the meter data all by itself. But they can help you identify problems and fine-tune operations. There's also the EMS approach to trending, which may not be as reliable as specialty data collection equipment, but can be an alternative, which is sometimes more cost-effective. So portable metering costs are normally reasonable when you're talking about just the equipment itself. That's not that expensive. I mean, the ESCOs have it and they use it over time. However, labor expense is a big variable. if you have to start flying around from island to island, taking measurements every year, spot measurements or annual measurements, you're going to spend some serious money on travel as well as programming, installation, data retrieval, and analysis. And that's usually why the idea of doing a lot of repeated measurements over a long period of time becomes cost prohibitive. So discrete metering is typically more cost effective, and spot metering is more common and long term. And you can use it with different M&V strategies. We've already talked about A and B, for example. But what a lot of people don't realize is even if you use option C with quote unquote dedicated utility grade revenue meters out there, you might still have to collect a lot of spot data with options A or B to make corrections to your option C approach. If a lot of things have changed, you're going to have to run around and do a lot of spot measurement or checking maybe or estimating. And therefore, you know, people say, well, option C solves all problems. No, not really. You still have to do a lot of measurements of other baseline related conditions to figure out what the meaning of the meter signal on your option or on your utility grade meter actually means. To interpret the data from that utility consumption, you have to understand all the underlying variables that are driving that consumption number and do like an analysis of variance on those variables to see which are the big ones, which are the little ones, how much impact they're having, when did they have it, how long did they have it, and it gets a little bit complicated. So with metering cautions, collecting valid data is essential. You want to focus on cost reasonableness rather than research. You know, I always say if I had an army of graduate students and, you know, equipment hardware was no issue, and I could basically pay the graduate students peanuts, you know, in money, and labor costs weren't an issue, then we can meter the heck out of everything. But that's not the opportunity that faces most agencies when they are doing these projects. Also, you want to convert units to dollars carefully, as we touched on earlier, to get the appropriate economic valuation of avoided utility costs. And fundamentally, you want to balance costs, the cost of M&V with the risk of the savings performance. And I'm actually going to stop here on slide 58 because this will take us into webinar number 2, where we'll cover slides 58 through 102, and we'll get into some more specifics on the DOTA M&V projects. So I want to ask you at this time, Larry and my audience, what did I leave out, or what else do I need to cover today, or are there any questions? All right, hearing none, I think that wraps up today's recording for our M&V webinar. I thank you all for your attention, and I look forward to seeing you next Wednesday for part 2.
Yes, and now let me add, Dave, that will be recorded also, and so there will be a recording available for the second half of this presentation.
Very good. Thank you.
Thank you, Dave.
All right. Bye now.